Welcome back to the deep dive. This is where we unpack complex ideas, try and pull out the really fascinating insights just for you. Today, we're diving into something that's, well, it's fundamentally reshaping how we design, build, and even live in our spaces. We're talking about the big shift towards building electrification.
Yeah, it's kind of a quiet revolution, isn't it?
Yeah,
But it's transforming everything from the air we breathe indoors to the stability of our whole energy grid.
exactly. It's about moving away from, burning fossil fuels right there inside our
Uh-huh.
buildings towards something cleaner, more sustainable. Okay, let's unpack this. Our mission today, really, is to take a proper deep dive into the specifics. We're going to use the latest updates from a real leader in green building, a LEED V5,
Mm.
and we're focusing right in on their energy and atmosphere credit, EAc1, which is all about electrification.
Right, that's the key one here.
So we want to explore the what, the why, and the how of electrifying buildings according to these, really cutting-edge standards, and what does it actually mean for cleaner air, lower emissions, a more resilient future for all of us.
Yeah.
And like you said, it's not just about saving a little bit of energy here and there. This is fundamental, changing the carbon footprint of our built environment. Before we really get into the weeds, if you find these kinds of shifts in our world as fascinating as we do, make sure you hit that subscribe button. You'll hear more deep dives into the topics that really matter, the ones shaping the world around us.
Okay, so let's start with the big picture. The elephant in the room, maybe.
Yeah.
The huge impact buildings have on climate change. It's often underestimated, I think.
Totally. People think factories, cars.
Right. But our homes, our offices, schools, hospitals, they're often burning fossil fuels right there.
Mm-hmm.
On site.
Natural gas furnaces, propane for hot water, oil boilers. Yeah, that direct combustion for heating, hot water, even cooking sometimes. It's a massive source of emissions, both greenhouse gases and, importantly, local air pollution.
And what's really fascinating here, and maybe gets missed in the broader climate talk, is that getting buildings off fossil fuels isn't just one strategy among many. Experts globally see it as one of the most impactful things we can do right now.
Really? One of the most impactful?
Yeah. Think about the sheer number of buildings, right? And they're always using energy. So electrifying them, collectively, it's huge. And that's exactly what LEV5's EAC1 credit is designed to push forward. It gives projects a clear framework.
Okay.
And the intent behind it, it's not just about carbon points. It's got layers of benefits. First off, the main goal is pretty simple. Cut down how much buildings rely on burning fossil fuels right there on site.
So practically that means no gas furnaces, no oil boilers, no propane tanks for the dryer.
Exactly. Electricity becomes the main and ideally the only energy source for those core functions.
Yeah.
No more flame in the basement, no gas line to the stove.
Right.
It stops those combustion byproducts being released right where people are. That's a big deal.
And that connects to the air quality point, doesn't it?
Absolutely. That's the second big benefit, and one people often feel directly. When you burn gas or oil inside, even with vents, it's not just CO2.
No, you get other stuff.
Yeah, whole cocktail. Nitrogen oxides, no-NOx carbon monoxide, formaldehyde, particulates, nasty stuff.
Which are linked to health problems.
Definitely. Respiratory issues, asthma, cardiovascular problems. NOx contributes to smog outside. Inside, studies link gas cooking to higher asthma rates in kids. So getting rid of that combustion cleans the air right where you live and work.
So healthier inside, cleaner air outside the window, that's a tangible benefit for communities.
Huge public health co-benefit. Imagine a whole neighborhood without that constant low-level pollution from heating systems.
Okay, so less dependence on fossil fuels, better air.
Hmm.
What's the third piece?
The third is about the bigger picture, supporting grid decarbonization and setting buildings up for long-term carbon-neutral operation. This is the future-proofing part.
How does that work?
Well, think about it. As our electricity grid gets greener, more wind, more solar, less coal, maybe even less gas power plants over time,
Okay.
an all-electric building automatically gets cleaner too, without the owner doing anything else.
Ah, I see. So the heat pump you install today runs on cleaner electricity 5-10 years down the line.
Precisely. You're not locked into a system burning fossil fuels that might get more expensive or face more regulations. Your building's carbon footprint shrinks as the grid cleans up.
So it makes the building more resilient, more adaptable to that energy transition?
Exactly. It keeps your investment valuable as we move towards decarbonization. Plus, there's this idea of grid interactive buildings.
What's that?
Buildings that can actually help the grid. Maybe they shift their energy use slightly during peak times using smart controls. They become assets, not just drains on the system.
Interesting. So pulling it all together then, What does this mean for the listener, whether they're a homeowner, a developer, or just someone living in a community?
Well, it means healthier places to live and work, thanks to cleaner air. It means we're collectively tackling climate change in a really significant way.
And your building is basically ready for a future powered by clean energy.
Yeah, it's about building better communities, fundamentally.
Hmm.
Quieter, cleaner, more resilient, more livable, one electric building at a time.
Okay, so the why is pretty compelling. Let's get into the how. LEV5 isn't just saying electrify, it's laying out a path, right? With points as incentives.
That's right, it's structured. And this specific credit, EAc1, is worth quite a bit, up to 5 LEED points. That makes it a really high-impact target for projects aiming for certification.
5 points is significant in the LEED system.
It really is.
Yeah.
And LEED offers 2 main ways to comply, 2 options, which gives projects flexibility depending on where they're starting from, what's feasible.
So it's not all or nothing.
Not necessarily. Option 1 is definitely the gold standard, or platinum standard maybe.
Okay, option one, what does that involve?
This one gets you the full 5 points. And it's tough. Absolutely no on-site fuel combustion from day one, period.
No gas, no propane, no oil, nothing burned on site for heating, hot water, cooking.
Nothing for primary functions. It's a full commitment to all electric for that building. A complete break from fossil fuels on-site.
Are there any exceptions? What about like backup power?
Ah, good point.
Mm.
Yes, there's a crucial exception for emergency backup systems. Your diesel generator for the fire escape lights or the hospital's critical systems that's allowed. Because that's about safety and resilience, not day-to-day operation.
Okay, that makes sense. Safety first.
Right. But beyond just no combustion, option 1 also has an efficiency requirement for the big energy users. Space heating and service water heating.
Ah, the COP thing you mentioned.
Exactly. Coefficient of performance. They need to achieve a weighted average efficiency of at least 1.8 COP.
Remind us what COP means again.
Sure. It's basically how much heating or cooling you get out for each unit of electricity you put in. Think of basic electric resistance heat, like a baseboard heater that's a COP of 1.0. 1 unit in, 1 unit out.
Okay.
Heat pumps, though, because they move heat instead of just making it, can get COPs of 2, 3, sometimes even 4 or 5.
Wow.
So requiring a COP of 1.8 means you can't just use inefficient electric resistance. You have to use efficient tech, mainly heat pumps. It's saying, go all electric, but do it smartly.
Makes sense. Are there nuances to that COP rule?
Yes, a few practical exceptions. For space heating, if you're in a really warm climate zone 0 to 2, think Florida, Hawaii, Southern California coast.
Where you barely need heating anyway.
Exactly. The heating load is tiny compared to cooling. So
Yeah.
they don't need to meet the space heating COP requirement there. It avoids unnecessary burden for minimal gain.
Mm.
Also, if you have a supplemental heating system that's only for very low temperatures, like a combustion backup for extreme cold snaps, that part is excluded from the COP calculation. Again, acknowledging practical needs and harsh conditions, as long as it's not the main system.
Right, for resilience.
And finally, for non-residential buildings, really small point-of-use water heaters, like under a sink, meeting specific HHRA 90.1 criteria, can be excluded. The energy use is just too small to mandate a complex central system for that specific spot.
Got it. So hitting all of that no combustion, 1.8 COP minimum, with those exceptions gets you 5 points.
5 points, yes. And achieving option 1 is actually a prerequisite for getting AD Platinum certification. So it really signals top-tier performance.
Okay, that's the high bar, but you said there's flexibility. What if a project just can't hit that full no combustion standard right away? Maybe it's a renovation, or the climate is super challenging, or the budget.
Exactly, and that's where LEV5 is quite pragmatic. That's option 2, partial electrification.
Partial electrification, how does that work?
It lets projects earn points from 1 to 4 points by electrifying specific major systems, rather than everything all at once. It's a way to reward progress and make it accessible.
Okay, so you can bite off chunks.
Precisely. Option 2 is broken down into 3 distinct paths. You can pursue 1, 2, or all 3.
What's the first path?
Path 1 is space heating. This one's worth 2 points. The main requirement is designing your heating systems to be electric, primarily using heat pumps.
Okay, electric heating. But what about those cold climates?
Here's the key flexibility. Combustion is allowed during extremely cold temperatures.
How cold is extremely cold?
LEDE defines it specifically for this credit, below 20 degrees Fahrenheit, which is minus 6.5 Celsius.
Okay, so below 20F, a backup combustion system can kick in without penalty.
Exactly. It allows for resilient design in places like, say, Minnesota or Maine, where relying solely on electrics might be challenging or overly expensive on the absolute coldest days. But the bulk of the heating still has to be electric.
Gotcha. Does this path also have the COP requirement?
Yes, but only in climate zones 3 and above, basically, everywhere that isn't those very warm zones we talked about. Where heating is a significant load, you still need that weighted average efficiency of at least 1.8 COP for the electric part.
Okay. So 2 points for electric space heating with a cold weather allowance. What's path 2?
Path 2 is surface water heating.
Yeah.
This one earns you 1 point. The requirement is electric domestic hot water systems.
Similar idea, heat pump water heaters.
Primarily, yes. And again, there can be exceptions for very low outdoor temperatures because air source heat pump water heaters can struggle a bit in extreme cold.
Right.
But this path has an interesting twist for larger systems, those over 34,000 backbrow or 10 kilowatt. Think central water heaters for apartment buildings or hotels.
Okay, what's the twist?
For those larger systems, you have 2 ways to comply. You can either hit that 1.8 COP minimum efficiency, encouraging heat pump water heaters, or you can show a domestic hot water solar fraction of at least 0.4.
Solar fraction, meaning?
Meaning at least 40% of the building's hot water demand is met by solar thermal energy, using rooftop collectors to heat water directly with the sun.
That's clever. So it's not just about how you use electricity, but also about integrating renewables directly.
Exactly. It's strategic. It recognizes that sometimes solar thermal is a great way to decarbonize hot water. It gives projects another pathway, especially if solar thermal makes sense for their location and design. It also boosts resilience.
Yeah, less grid dependence for that load. Okay, so that's 1 point for water heating. What's the third path?
Path 3 covers cooking and process loads, also worth 1 point. This requires electric cooking appliances, electric laundry dryers, and any other electric process equipment. No gas stoves, no gas dryers.
So induction cooktops, electric ovens.
Yep. Which, by the way, often improves indoor air quality and can be very efficient.
Interesting point about this path.
A very practical one.
Yeah.
If a project doesn't have these kinds of systems, say an office building with no kitchen or laundry, or apartments where tenants bring their own appliances, they automatically get this point.
Oh, that's smart. So you're not penalized for not having systems you don't need.
Right. It simplifies things for certain building types. And again, there are exclusions for very specific low-temperature process heating equipment. It focuses on the main combustion sources.
Okay, so summing up option 2, you can get 2 points for space heating, 1 point for water heating, and 1 point for cooking process loads for a total of up to 4 points.
Correct. You can mix and match based on what's feasible. It allows that incremental progress.
So it's a really clear structure. Go all in with option 1 for 5 points and the platinum requirement, or take steps with option 2, grabbing points along the way. It makes electrification feel much more achievable across the board.
That's the idea, a pragmatic roadmap for a necessary transition.
Okay, we've got the options, the points, but let's circle back to that COP metric, the coefficient of performance. You mentioned demonstrating it. How do project teams actually do that? What are the technical ways to prove you're hitting that 1.8 target?
Good question. Because, yeah, you can't just say we use heat pumps. You need to document it. LEED-BD+C gives 2 main ways to calculate and verify the COP.
2 methods. Okay.
Method 1 is using rated conditions. This means you look at the manufacturer's official specifications for the equipment you're installing.
Like the sticker on the side of the unit?
Sort of, but usually it's more detailed technical documentation.
Right.
These ratings are done under standardized lab conditions, so you can compare different models fairly.
And you mentioned specific temperatures.
Right. For heating, especially with air source heat pumps, you need to look at the COP rating measured at an outdoor air temperature around 17 degrees airfare, which is -9 Celsius.
Why 17 Fahrenheit specifically?
It represents a pretty common cold weather operating point where efficiency really matters. It's not the absolute coldest, but it's challenging enough to be a meaningful benchmark for winter performance. And if you're using ground source or water source heat pumps, you look at ratings based on the source temperature, typically around 44 degrees air, 6 degrees C, because the ground or water temperature is much more stable than air temperature.
So you use these specific, relevant, rated values from the manufacturer.
Exactly. It's a standardized way to compare theoretical efficiency.
What's the second method?
The second method is using energy simulation. This is often used for more complex projects. You use sophisticated computer software.
Like Energy Plus or similar tools?
Yeah, those kinds of tools. You build a virtual model of the entire building, including its heating and cooling systems, insulation, windows, occupancy schedules, local weather data, everything.
Wow, detailed.
Very. And the software simulates how the building and its systems perform over an entire year, hour by hour, or even faster. From this simulation, you can calculate the annual average COP for your heating and water heating systems.
Ah, so instead of one rating at one specific temperature, you get an average across all operating conditions throughout the year.
Exactly. It gives us a more holistic, real-world picture of performance, considering part load efficiencies, how systems interact, everything. It captures the dynamics.
That sounds more comprehensive, maybe more accurate.
It can be, especially for complex systems or buildings designed with integrated strategies.
So why have both methods? Why not just require simulation?
Flexibility, again, simulation is powerful, but it's also complex and requires expertise. Using rated conditions is simpler and might be perfectly adequate for smaller or more straightforward projects. Offering both methods lets teams choose the approach that best fits their project scope and design process, while still ensuring robust, verifiable data.
Makes sense. Provide pathways, not roadblocks.
Now, speaking of specifics, let's nail down that low temperature definition again. For option 2, path 1, where supplemental combustion is allowed for heating. You said it was below 20 Fahrenheit.
Yes, that's absolutely critical. For the purposes of this specific credit, EAc1 low temperatures means outside air temperatures below 20 degrees Celsius or minus 6.5 degrees Celsius. That's the hard line. So it's not just when it feels really cold. It's a precise, measurable threshold.
Precisely. It provides that clear boundary for when that flexibility for resilience kicks in, mainly for colder climates. It prevents the exception from becoming a loophole, ensuring the main goal of electrification isn't undermined. You still need to design the electric system to handle the bulk of the load above that temperature.
Okay, crystal clear. Now, buildings aren't always simple standalone boxes. What about more complex situations like district energy systems or maybe technologies like fuel cells? How do they fit in?
Great points. The energy landscape has these complexities. Let's take district energy first.
Where one central plant serves multiple buildings.
Right. If your project gets its heating, cooling, or hot water from a district energy system, that system itself generally needs to comply with the electrification requirements of this credit.
So the central plant can't be burning gas. Essentially, yes. Or the project needs to follow specific broader LED guidelines for district energy systems, which have their own assessment criteria. The key takeaway is you can't just push the fossil fuel burning off-site to a shared plant down the road and claim your building is fully electrified under this credit. The intent is to remove that combustion from the building's energy supply chain.
Okay, so the source matters. What about fuel cells? They sound kind of green, right?
They often are discussed in that context, yeah. But here's a crucial distinction for EAc1. Fossil fuel-based fuel cells do not qualify.
Even if they're more efficient than burning gas directly.
Even then, because they still inherently involve processing and effectively combusting a fossil fuel like natural gas on site to produce electricity and heat. The credit's core aim is zero on-site fossil fuel combustion for primary operations. So even efficient combustion via fuel cell running on fossil fuels doesn't meet that specific requirement. It really underscores how focused this credit is on a complete break from on-site fossil fuel use. That's a really important clarification. It's about the source of the energy on-site, not just the efficiency of its conversion. Okay. So if someone listening is thinking, right, I want to electrify my next project, or maybe even their own home renovation, what are the real keys to success, the best practices to make it work well?
Absolutely. Beyond just meeting the LEED requirements, there are definitely some smart moves, best practices that come through in the LE guidance and general industry knowledge.
Lay them on us.
Number one, maybe the most critical, start early. Integrate electrification right from the very beginning of the design process. Don't tack it on later.
Why is starting early so important?
Because trying to retrofit later is almost always harder and way more expensive. Think about designing the electrical panel capacity, the ductwork pathways, the space for heat pump equipment. If you plan for it from day one, it's integrated smoothly.
Right.
And starting early means you can optimize the building itself first. Super insulation, air tightness, high-performance windows. Reduce the heating and cooling load dramatically before you even size the electric systems. That means smaller, cheaper, more efficient heat pumps. It's about integrated design.
Design the thermos before you choose the heater.
Exactly. Get the architect, engineer, builder talking about electrification from the initial concept sketches.
Okay, start early. What's next?
Second, use high-efficiency electric heat pump technologies. These really are the workhorses of modern electrification for heating, cooling, and hot water.
Not just basic electric resistance.
Definitely not. Heat pumps, as we said, move heat. They don't just make it from electricity. Their efficiency, their COP, is just fundamentally higher, and the technology has improved massively, especially cold climate heat pumps that work effectively down to very low temperatures. And heat pump water heaters are a game changer too.
So lean heavily on heat pump tech.
Absolutely. It's the most efficient way to use electricity for heating and cooling.
Okay. Third best practice.
Incorporate renewable energy sources, especially solar PP panels on site.
So electrify the building and generate your own clean power for it.
Yes. Electrifying eliminates on-site combustion, which is great. Adding solar PV means you're directly offsetting the electricity you do use with clean, zero-emission power generated right there.
Moving towards net zero energy.
Potentially, yes. Or at least significantly reducing the building's overall carbon footprint. It also boosts energy independence, lowers operating costs because you're buying less electricity, and adds resilience, especially if you pair it with battery storage. It's not just about not burning fossil fuels, it's about actively generating clean energy.
Makes sense. Electrify and power it cleanly. What's the final key practice?
Finally, consider smart controls and energy management systems. These are becoming crucial.
Beyond just a programmable thermostat.
Oh yeah. Think building automation systems, BAS, or energy management systems, EMS. These can optimize when your heat pumps run based on weather forecasts, occupancy, even electricity prices. They ensure you're getting the most efficiency and comfort.
And you mentioned grid interaction.
Right. Smart controls enable buildings to participate in demand response programs. The utility might signal high demand, and your building automatically adjusts its thermostat slightly, or shifts water heating to reduce load, maybe earning you incentives. It makes the building an active, helpful part of a smarter, cleaner grid.
So the building becomes intelligent and interactive.
Exactly. Efficient, smart, and grid-friendly. Those four things start early. Use heat pumps, add renewables, use smart controls. Those are really key to successful high-performance electrification.
That's a great set of actionable strategies. So let's bring it all home. We started by talking about why this shift is happening, why it matters so much. It feels important to really anchor back there. This isn't just technical jargon or points on a checklist.
Absolutely. It's worth reiterating the big picture impact. When you boil it all down, what does electrification achieve? First, as we said, it eliminates direct fossil fuel combustion right where people live and work. That's the fundamental environmental win. Stop burning stuff in buildings.
Cleaner air immediately.
Leads right to the second point. Significant reduction in carbon emissions. Buildings are a huge piece of the climate puzzle. Electrifying them, especially as the grid gets cleaner, is a massive lever for climate action. Huge impact when scaled up.
And the third.
The improvement in air quality, both indoors and outdoors. Fewer pollutants mean healthier people, healthier communities. It's a direct public health benefit that often gets overlooked, but is incredibly important.
Okay. And the future-proofing aspect.
That's the fourth key point. Ensuring building resilience as grids decarbonize. An electric building is ready for the future. It's less exposed to volatile fossil fuel prices. Its environmental performance actually improves over time as the grid adds more renewables. It aligns your investment with where the energy world is clearly heading.
So it's about protecting value, reducing risk.
Definitely. You're creating spaces that are healthier, cleaner, more adaptable, and ultimately more valuable in the long run. It's not just about getting a LEED D point. It's about smart, sustainable investment. Like source material says, electrify today, power is sustainable tomorrow. It sums it up well.
It really does. So today we've really dug into how LEED v5 is pushing this forward, setting clear paths for buildings to become cleaner, healthier, more resilient. We looked at the big why climate, air quality, future-proofing, and the details of LEED's options, the points, the technologies, the best practices, showing that whether you go all in or take steps, progress is possible and rewarded. It makes you think, doesn't it? If every new building, maybe even lots of existing ones, could just stop burning fossil fuels on site, what would our cities and towns feel like?
Cleaner air, definitely. Quieter neighborhoods without furnace rumble. More energy independence, maybe.
Yeah, and what if those buildings weren't just energy consumers, but active players in a smart grid, helping balance renewable energy?
That raises a huge, important question for the future, doesn't it? As millions of buildings electrify, how does that change the demands on our electrical grid?
Right.
And what innovations in energy storage, grid management, maybe even localized microgrids will we need to meet that demand reliably and sustainably with even more renewables? It's a massive engineering and policy challenge, but also a huge opportunity.
A dynamic future for energy. Well, we hope this deep dive gave you some powerful insights, maybe sparked some new questions about how our built world is changing so rapidly. If you are curious about how our world is evolving and you want more deep dives into fascinating topics just like this one, please don't forget to subscribe to our show. You'll hear more about this world and the chefs that are defining our future. Thanks for joining us, and we'll catch you on the next deep dive.